ARRHENIUS definitions of acids and bases. Any species that produces hydrogen or hydronium, which is H3O plus, in solution is going to be considered an acid. And according to this definition, any base will consist of anything that will produce hydroxide ions in water. This is the most basic of the acid-base definitions. And for our purposes, you'll see us probably more frequently using the Bronsted-Lowry definition. Basic idea here, have your hydrochloric AQ. What's happening here, it's dissociating into its H plus ions and the chloride ions, so producing those hydrogen ions in water. And for the, say it's lithium hydroxide, which happens to be one of the strong bases, so it's going to dissociate into the lithium and the hydroxide ions in water. Okay? Break apart completely dissociate. Basic idea here. Yes?
The first equation, is this
H2?
Yeah.
Oh, no, this is AQ, so the hydrogen is dissolved in the water. It's not actually a gas. It would be H2 if it was a gas and it was bubbling out of solution, then we would put it as diatomic. But here, the H plus ion is dissolved in the water, reacting with the water. So it's not hydrogen gas. It's actually just hydrogen ions floating around in the water. Right, the Bronsted-Lowry definition, we're looking at the donor-acceptor idea. Now, we call it a proton donor, as I explained earlier, that, hydrogen, an atom of hydrogen has one proton and one electron. When it loses that electron, it becomes H+. It is now simply just a proton. So H+ and proton go hand in hand. So when we really say proton donor for the acid, we're saying it's an H+ donor, donating one of those hydrogen ions. The base, on the other hand, is going to accept hydrogen ions. Okay? For a strong acid-base reaction, you see the net ionic here that we talked about before, where you have the one hydrogen ion being added to the one hydroxide ion, and you get 1 mole of water. But if you have something that is not it's not necessarily a strong relationship here, where you would have some neutralization going on. You could have, something like your ammonia with your hydrochloric. Okay, what would you get out of that? You probably saw this in the problem set. The hydrochloric is the acid here. It's going to donate the hydrogen over to the ammonia. When it does that, the NH3 picks up the hydrogen and becomes what? Ammonia. So it ends up becoming ammonium over here, and then, the chloride. However, this would be like the molecular equation, but since we know ammonium and chlorides together are soluble based on our solubility rules, we would probably write them separated with their AQ like so. Okay? In this case, the ammonia is considered the base because it's accepting the H. The hydrochloric is the acid because it's donating the H. So we're going to see a lot of other combinations, and ammonia is the weak base here. We're going to look at weak acid-base equilibrium and chemistry during Unit 4. Unit 4 is when we're going to really get into all the acid-base chemistry and looking at the weak stuff. The strong stuff is primarily the stuff that we did last year, and it's also what you're going to see in the problem set and on this test, that basic neutralization one that we did last year in titrations from last year. That's what we're focusing on Unit 1. We'll get to the weak combination stuff in Unit 4.
Hydrochloric acid is a strong acid that completely dissociates to form H+ and chloride ion in solution. The H+ ion is rapidly solvated by water, forming the hydronium ion as shown. The hydronium ion reacts with the hydroxide ion from the dissociated strong-based sodium hydroxide to form water. In this neutralization reaction, sodium and chloride are spectator ions that do not participate in the reaction.
Okay, so this is a good representation looking at the little circles. Let's watch it one more time. So you can pay attention to like these ones right here. I don't know if you can see that right there. Let me type on it. But that one has the 2 H's to the 1 O. But right when they drop the acid in, some of the H's attach themselves to the water, forming hydronium. Then when they drop the base in there, the OH pulls that H back off and neutralizes it back into water. Okay? So I don't know if we can watch that again real quick and you can pay attention, see it.
Hydrochloric acid is a strong acid that completely dissociates to form H+ and chloride ion in solution. The H+ ion is rapidly solvated by water, forming the hydronium ion as shown. The hydronium ion reacts with the hydroxide ion from the dissociated strong-based sodium hydroxide to form water. In this neutralization reaction, sodium and chloride are spectator ions that do not participate in the reaction.
Okay, so hopefully you saw, that the hydroxide came in, it had just the red circle with the little one, and so then it picked off one of the little blue circles off of the hydronium and went back to neutralizing, although water does self-ionize. So you do have a little bit of hydronium and a little bit of hydroxide in all water because it's constantly reacting, it's dynamic. Okay, but it's such little amounts that it goes back to equilibrium, and this is about equilibrium stuff too, which we're going to get into in Unit 3. Okay, but just paying attention to the molecular level here, is getting a good idea at any time because they love to make you draw the stuff for the AP exam. Okay, so all molecular level stuff is very important. Now, performing calculations for acid-base reactions. You might have been taught like the formula last year, but we're really, because we're at AP now, we're going to try to stick to stoichiometry because mole to mole and looking at reactants and products and as so much easier than trying to memorize formulas and plug and chug because you can work things in a train track from various angles if you know how to set up the molar relationships. Okay. So first, of course, before you look at here, you want to decide what's occurring. You want to write out the balanced net ionic, calculate the moles. Like I said, if there's nothing else you can think of to do, go to moles. You can always go someplace from moles. Determine limiting where appropriate, calculate moles of required reactant or product. And then if you need to convert it to grams or volume of solution, depending on what it's asking for. So what volume of a 0.1 molar HCl, I know that looks like a 1, it's supposed to be an L, solution is needed to neutralize 25 milliliters of 0.35 molar sodium hydroxide. So what should I do here first? What did it just going to do? Write out the reaction, right? Let's look at the reaction. We have strong acid, we have strong base. So what's our net ionic going to be here? It's going to be what? H plus OH gives us H2O liquid. And yes, you would write in your AQs like so. Okay? Now the chloride and the sodium are spectators. They're not really reacting, so we don't really have to pay attention to them. But this is a nice, easy molar relationship because in this case, strong, we have a monoprotic acid. Everything is 1 mole to 1 mole to 1 mole. We don't have a diprotic or a triprotic acid where you have extra H's attached. Nor do we have where a base that has 2 hydroxides attached, because then you have to really pay attention to the molar relationship. So here, my starting amount, what volume of the 0.1 do I need? The first thing I need to figure out is how many moles of the hydroxide that needs to be neutralized. Okay, so let's go there. So, starting with our 0.0250 liters, 0.350 moles per 1 liter. This is of the hydroxide, because I don't really even need to write out sodium here. Then I can diagonal down my 1 mole of hydroxide, because now I can go to how many moles of H plus, moles of hydrogen. Okay. Does anybody see after this point where can we go? What do we need? Volume. What else do we have? What other piece of information? What does molarity tell us? Moles over liters, right? So if I diagonal down my moles of H plus, I can go to liters, right? 1 liter equals how many moles? Right? So see how it goes in one nice big long track here. So then we know how many liters of the 0.1, and if you look at it, the concentration of the hydroxide is higher. So what would you expect the volume to be? Equal, below, or above the 25 mark? If you have 0.35 molar of sodium hydroxide and only 0.1 of the acid, do you think you'd need less volume, more volume, or what? Because the acid is weaker, you're going to need more of it, right? So you're looking for a volume that should be greater than 25, right? At least triple and a little bit extra, right? So kind of use that number sense to your benefit, thinking of, well, the concentration of the acid is less, so and it's 1-to-1, that means I'm going to need more of the acid than the volume of the base. And what do we end up getting here? .0875 liters, or you can make that 87.5 milliliters of HCl. Either or. Since the beginning amount of the titration, and we use our burettes, are usually in milliliters, you would want to, convert it back to the milliliters. Okay? Because you're going to have to mentally convert it anyways to put it in the burette if you were doing a titration. So there you have it. Good. All right, now, I already see something when I look even at the first sentence. A certain experiment, 28 milliliters of 0.250 nitric is, and 53 of 0.32 potassium hydroxide are mixed. What happens when we have both reactants like that again? It's going to be a limiting one, right? What is the concentration? Oh, calculate the amount of water in grams, so limiting. Then it also wants an excess. Oh, yay, fun, kind of like you did on the quiz, but now with acids and bases, right? So once again, looking here, we have strong combination because we have nitric plus potassium hydroxide. Okay, so basically these guys end up spectating, and what do we end up getting? Water. So it's really just H plus OH minus, giving you water as your net ionic equation. Right? Okay, so hopefully you'll start getting to that point where you'll see, oh, nitrate, spectator, cross it out. Oh, potassium, alkali metal, spectator, cross it out. Yeah, so you'll start recognizing them faster. being able to get to that net ionic faster. But because we have both reactants, we need to work them both to the water. Everything up there in the reaction is going to be how many moles? 1 to 1 to 1, so everything's 1 mole. It's good. So we can just set up our two tracks here. 0.028 liters. Diagonal down my 1 liter. Moles. This is of the H plus. Okay. 1 mole of H plus gives me 1 mole of water, right? And has anybody got to that point where they know water's molar mass off the top of their head? Good, you guys are great. 1 mole of water, 18.02 grams water. Very good, very good. So that's one of them. The other one is very similar, except for instead of hydrogens in there, it's going to have hydroxides, and the numerical values that we started with are different. So let's set that one up too. We have 0.0530 liters of 0.320 moles. This is hydroxide this time. Equals 1 liter. 1 mole of hydroxide to 1 mole of hydrogen. Water. 1 mole of water. And then our 18.02 grams. All right. So we look for the one that comes out less. The one that comes out less is going to be our theoretical yield, and also will tell us which one's the limiting reactant. What did you guys get for the first track? 0.126. Yes? Oh, not moles, grams, right? You worked it to grams, correct? Okay. And the one down here? .306 grams, right? I think that's what I heard you guys say, right? You want to put the 0 in there. Okay. So which one is our theoretical yield? This one's our theoretical yield, so this is the amount produced, so that's what we want for the answer there. Also, which one is our limiting? The acid is the limiting reactant, so that means the base is the excess reactant. So when we're focusing on which ions are in excess, now we know to look for the hydroxides. Because the problem is which one's going to be extra? Well, we know it's going to be the hydroxide because we figured that out from the first problem. So now we go to figuring out how much of the hydroxide is still floating around in the water. So just like you did earlier on the quiz, what should I do with my hydroxide first to start this process? Figure out the moles I start with, how many I'm starting with, right? So we are starting with 0.053 liters, 0.32 moles hydroxide. It's 1 liter. So this is going to be my moles of hydroxide that I'm starting with. I'm starting with 0.01696. I'm not going to round till the end. Okay. This is my moles of hydroxide, starting amount. Now what can I do? Correct, I can figure out from how much was produced here. I can start working that towards my hydroxide, and that'll tell me how much of the hydroxide was used in the water. Correct. Good thinking there. So let's do that. We'll take our 0.6 grams water. 18.02 grams equals 1 mole water. And 1 mole water is 1 mole of hydroxide, because everything was 1-to-1, right? This is going to tell me my amount that was used in the water. And that gives us whatever, okay? This is the used amount. So I just need to subtract these two, and that's going to be the moles still left over floating around in the water. So I leave my calculator amount in here, and I'm just going to take my 0.01696 and subtract my answer. And that will give me the moles left over. Whatever, it keeps going on and on, so I'm just going to leave it. This is my difference. Then what do I need to do with my bottom amount to get that concentration? I need to calculate the new volume, right? I had 53, what was the other milliliters? So it was 28 plus 53, right? 28 plus 53. So this is 81.0810 liters. And what's our concentration? What was it? So it's very similar to what you have already done, but now we're just dealing with H's and OH's. Yes?
Instead of doing two different, can we just subtract the excess amount of water to the limit and then just go by the mole?
You can. That is another way to do it. If that's more comfortable for you, you can. I'm always a starting and used up amount kind of person, but there are multiple ways to work limiting and excess reaction problems. And we got it right, so that's good. All right, titration, equivalence point, endpoint, words from last year. And we're going to do a titration after the first unit test. It's going to be a redox titration, though. It's going to be similar to what you've already done, but it's not acid-base. It's going to be a redox reaction, which is kind of cool. Delivery of a measured volume of a known concentration, which is the titrant, into a solution containing the substance to be analyzed, the analyte. So the stuff in the flask that you're putting it into, you don't know the concentration of that. You're trying to figure it out. The equivalence point is going to be exactly where the moles equal the moles. Okay, so make sure that you do understand that. Enough titrant is added, but we're talking moles of the titrant equals the moles of the analyte there at that equivalence point. Okay. Now, the endpoint is when the indicator changes color. Now, the problem is that, yeah, you can use like a pH probe if you're doing an acid-base one, and it will give you exact numerical value. You don't really have to have the indicator color in there because you're using the probe. But in our redox one, we're going to be looking for a color change because we're not measuring pH, we're actually measuring the redox reaction itself, which we're going to talk about at the end of this PowerPoint too. So you're going to be looking for when the indicator changes colors. And on acid-base ones, you can use indicators rather than just the probes that we used with Logger probe. The problem is there's so many indicators out there that you have to choose one where the endpoint of your indicator is going to be close to your equivalence point. based on your acid-base combination. And we're going to get into all of that when we get into Unit 4 with the acid-base chemistry. But for our purposes, we're going to be using a purple substance called potassium permanganate. It's purple color. And when it reacts and with the other things, it will stay clear. Okay? And then when you've added just enough potassium permanganate, your flask is going to flash purple, or the pinkish color that it is. So you'll be able to tell that you've gotten to that moles equal moles point. We're going to look at that lab, after the Unit 1 test. Okay, doing that one. Get out the burettes and all that good stuff. So for our purposes, we're doing a titration. It's going to be a redox titration, but we'll still be looking for that indicator color change. Okay. Redox reaction. Reactions in which one or more electrons are transferred. So we're looking for the change in the charge, because that tells us that the electrons have moved. Okay. Looking for that movement of electrons. We're going to go over a bunch of new words, old words, some words, I don't know. I know for most classes you get about 1 day of redox in honors or even regular chemistry. So you didn't get a whole lot last year. So we're going to go pretty in depth, and you do have to go back to knowing all of your periodic table charges, polyatomic charges, and then there's a few new oxidation numbers on here. And the oxidation number is basically the charge provided to show how many electrons are either gained or lost by that element. So let's look here. This is the sodium and the chlorine reacting to make sodium chloride. Two totally different elements, very reactive in water sodium. With chlorine gas, it's pretty toxic and it's yellowish green or whatever. You would think these things we would never want to put on our food and eat it, but when they combine together, we get salt out of it. But I don't know if you remember this reaction from last year. This is one of our synthesis ones. And it would be balanced like so. But individual elements, their charges, when they're in their elemental form, are 0, right? They haven't exchanged any electrons. And if you remember, your charges for sodium and chloride, you would remember that this goes to +1, this one goes to -1. So if you're really looking at the redox happening here, sodium went from 0 to +1. What does that mean about sodium? It lost an electron. And the chlorine went from 0 to +1. I mean -1. 0 to -1. So it gained an electron, and then to balance our atoms, it would be 2 sodiums with the 1 chlorine diatomic molecule. And so actually it ends up being a transfer of 2 electrons, because you need 2 sodiums, each transferring 1 to the 1 chlorine diatomic molecule to get your 2 sodium chloride crystals. Okay? Or, formula unit there. So this is kind of what we're looking at. We're talking about redox. So we use 2 ways to remember. Oil rig, that's the one I use. Oxidation is loss of electrons. And rig is reduction is gain of electrons. Now, some people like Leo the lion says grr, but if you think of Leo as a lion type, going grr. Lose electrons, oxidation. Gain electrons, reduction. You can use that one too if that one's easier for you to remember. So I prefer oil rig myself, but Leo grr works too. Lose electrons, your oxidation. Gain electrons, your reduction. Okay? Either or, should be fine. So some other key words before we get to balancing and such. Redox characteristics, we transfer electrons transfer may occur to form ions. Oxidation is an increase in oxidation state or loss of electrons. Reduction is a decrease in oxidation state, which means gaining electrons. The oxidation state is actually just a number assigned to the atom representing the degree of loss of electrons. So it's that charge number we assign to it, and it's normal, number that it goes with. Like oxygen's oxidation number is -2. So oxygen as an element, usually has those 2 extra electrons on it, and we now measure oxygen from that -2 point. Is it gaining or losing from that -2 point? And if you remember from last year, the oxidizing agents and the reducing agents are actually kind of reversed. So an oxidizing agent would be the reactant that causes oxidation. So it's actually the one being reduced, because it's actually taking electrons away from another atom. And by doing so, it's causing the oxidation from that other atom. And vice versa with reducing agent. The reactant that causes reduction, though that's the one being oxidized. So I'm the reducing agent. That means I'm giving away electrons to another atom. That means I'm, causing that atom to have to gain those electrons, and therefore that atom's being reduced. So they're kind of the opposite, of what you would think of. Something being oxidized is going to be the reducing agent. Something being reduced is going to be the oxidizing agent. And we're going to kind of move quickly through our assigning charges here. And I will go through the oxidation numbers. They're listed there on your sheet for you, so you do not need to write them down. Okay? But as before, as I showed you with the sodium and the chlorine, they both, because their elemental forms are assigned to 0. Oxidation of any monatomic elements usually follow the charge of the ion from the periodic table. So like the alkali metals, potassium, lithium, sodium, they're always +1s, unless they're in their elemental form. So if they're in a compound, they're going to be +1 though. Oxygen's -2, except for peroxides, which we rarely use. They're -1. Hydrogen is the toughy one to recognize. If hydrogen is in a covalent compound, that means with other nonmetals, hydrogen's going to be +1. If it's in a hydride where it's within metal, it's going to be the -1 charge. That's more rare. Hydrides are more rare. You're going to see hydrogen more often in with other nonmetals. Fluorine is -1. And the sum of the oxidation states needs to add up to 0 in compounds. But if you have a polyatomic or a charge on a compound, then you know that your sum needs to add up to that charge on the compound. So following these rules, many elements aren't going to necessarily follow their normal charge, especially if they're not in their anion position. Like if chlorine is in the front of the compound and it's not the end of the compound, if it was at the end of the compound, it would be chloride and it would follow the -1. But if it's in the beginning of a compound, it's going to follow another charge. So looking here, these are some of the ones. I'm going to work out a couple of them for you to look at. So this one's potassium dichromate. There's lots of things going on here. Okay. The potassium, I'm going to write it bigger over here. The potassium is going to follow its +1 charge because that's what it only has the ability to do. The oxygen, as you saw in the rules, is always going to be -2 unless it's in a peroxide. This is in a peroxide. So off of that basis, I can figure out part of the total. The K is going to, because there's 2 of them, is going to bring in a +2 charge. The oxygens are going to bring in a -14. Does everybody see that? Because there's 7 of them, each one counts as a -2, so therefore we have a -14. Now the chromium is one of those multiple oxidation metals, definitely has many different charges, so we have to figure out which one it's going to be in this particular case. So What's plus 2 and minus 14 going to give you? Negative 12. That means out of the chromiums here, we need a plus 12 out of those chromiums because this has to add up to 0. There's no charge on this compound, so it needs to add up to 0. So if there's 2 of them, what does each one have to be worth? Plus 6. Good. So in this case, the potassium's a plus 1, the chromium's going to be a plus 6, and the oxygen's going to be a minus 2. When it wants oxidation numbers, it wants the individual numbers, not the totals, by the way. I use the totals to figure them out, but it doesn't want me to say chromium's worth plus 12 there. Each chromium is worth a plus 6. That's the oxidation number on the chromium. Okay, now let's look at the carbonate. Like the carbonate one, because it adds up to a what? Negative 2. So now we want the charges to add up to a minus 2 here. So the only one that we know from our oxidation rules there is oxygen, right? So oxygen is worth a, in and of itself, it's worth a minus 2, and there's 3 of them, so that equals minus 6, right? So the carbon in this case is going to be something plus the negative 6 has to equal minus 2. So in this case, what would the carbon need to be? A plus 4. The carbon would need to be a plus 4. So the oxidation number of the carbon is plus 4. The oxidation number of the oxygen is minus 2. And that's when it has a charge on it, just make your oxidation numbers add up to that charge. Okay? MnO2. That one should be pretty easy because we've been working with oxygen a lot here. Oxygen's minus 2, right? So that means this is a minus 4, right? In that case, the manganese needs to be a, so the manganese here should be a plus 4, right? Now, as you see in the PCl5, that's phosphorus pentafluoride. That's a covalent compound, right? Okay, covalent compound are like, what is charges? No, remember, these are oxidation states, just a number assigned to keep count of the electrons. This case, the Cl's in the second part of the compound. When it's over here in the second part of the compound, it follows its normal charge. In this case, it's going to be a minus 1. And there's 5 of them, right? So that's a minus 5 total. But there's only one phosphorus. So in this particular case, phosphorus would not follow a minus 3 charge like you would think off of the periodic table. In this case, the phosphorus would need to be a plus 5. So the P in this case would be a plus 5. So always work off of the one that's in the last position of the compound. I would start there. Unless it's a polyatomic like here, you can figure out this one, you can figure out that one, and then use those to figure out the middle element. And also here is sulfur tetrafluoride, another covalent compound we still have to assign the charges to. The fluoride part is in the last position. I'm going to give it its minus 1, so this equals minus 4 together. So in this case, the sulfur is going to carry what oxidation number? A plus 4. Very good. Okay. So that's what we're going to be looking at there. So go ahead and spend, 2 minutes or so looking at exercise 14 and see what you come up with. It looks like some people are getting done here. Oxygen's always a minus 2, so I'm going to put that there, although this would mean that's a minus 4. So in this case, C is going to be a plus 4, O is still going to be a minus 2. Okay. Sulfur hexafluoride is different than sulfur tetrafluoride because in this case, the fluorine's still carrying that minus 1, but together that makes that a minus 6. So in this case, your sulfur needs to be a plus 6. So it added a extra 2 to that. So fluorine still carries the negative 1 charge. Nitrate. Oh, this one's fun. Oxygen, still -2. This makes up -6. But remember, our total needs to add up to -1 here. So in this case, if there's only one nitrogen, what plus -6 is going to give me -1? So in this case, the nitrogen is a +5. The oxygen still carries the -2 oxidation number. When you're given this big old huge paragraph, yeah, okay, lots of reading. Powdered aluminum is pulverized in iodine crystals, drop of water added to help it go along, and you get this energy and the aluminum iodide out of it, right? For this, all of that mess, we have to find what's being oxidized, what's being reduced, then the oxidizing and the reducing agents. First thing I would do is assign my charges to everything in the reaction. Aluminum by itself gets a, elemental aluminum is 0. Elemental iodine, which is diatomic, still gets a 0. In this particular compound, aluminum follows its normal cation charge. The iodine is going to follow its normal anion charge. So this would be -1, and this is going to be +3. Once you assign the charges, you can see the direction. The aluminum goes from 0 to +3. Is that being oxidized or being reduced? Okay, so this one, aluminum, is being oxidized. That also tells me that aluminum is causing the reduction on the iodine. So it is also the reducing agent. See how that works? Okay. Looking here at our iodine that's going from 0 to -1. You can tell that it is being reduced. So I is being reduced. And actually, in this case, the I2 is being reduced, and it is going to be your oxidizing agent. Okay. Now, if you're looking at exercise 16, there's 2 separate reactions, but we would do the same thing here. We are going to just assign the charges, determine what is being oxidized, what's being reduced, and what the agents are. Now there's just slightly a little difference. In this case, both of our reactants were simple elements, so those are going to be the agents. But in the next one, we do have the second one here. This one just has elemental oxygen. These are 2 separate compounds. So the entire compound is going to be considered part of the agent, not just the element itself that's doing the redox part. So you go ahead and mentally assign your charges. I'm going to go ahead and assign them as I see them too. Elemental I always do first because they get the big zeros. They're pretty easy. Oxygen's easy, so I'm going to assign those. Right? Oh, lead gets a 0. Because it's just by itself. Now I go look for the more difficult ones to assign. Oh, I forgot an oxygen over here. There we go. So that means this lead's a +2. That means that lead's +2. That means this sulfur is a +4. That means that carbon's a +4. Here on the lead-2 sulfide, we're just going to follow its charge of -2. That means this one's going to be a +2. And oh, here in the carbon monoxide, look at the carbon. What is it going to be? A +2. Good. So simply assigning them, figuring those out, and you can look here. So looking here, we see that the oxygen is going from 0 to -2. So that one's being what? Reduced, right? So O is being reduced. And O2 would be the, oxidizing agent. And looking, who is the other one up there changing charge? The sulfur goes from -2 to +4. The lead's not changing charge, so it's not really participating in the redox. So the sulfur is going to be being oxidized, but the PBS is going to be the reducing agent. So the entire compound is considered the agent. You see what I'm saying? The element being oxidized, though, is the sulfur. But the entire compound that begins on the reactant side is considered the agent. So down here, looking at this one, who changes charge? Carbon and lead. So the lead goes from +2 to 0. What's happening there? That's reduction, yes. It's gaining electrons because it's becoming more negative. That means the PBO is the oxidizing agent. Okay. The oxygen itself is not changing, so that's not part of the redox, but the carbon did go from +2 to +4. So the carbon is being oxidized, and the CO is therefore the reducing agent. All right, now for regular ones without needing water, they're just like balancing regular reactions. So for this example, balance the reaction between solid zinc and aqueous hydrochloric to produce zinc 2 chloride and hydrogen gas. So we would start out by writing the molecular equation just like we normally would, right? Just like you did in the other equation chemistry, right? And why I say we don't need water here, because there aren't any oxygens in the reaction. You don't see any oxygens up here, so we wouldn't need water. Okay? So after you write out that lovely, nice, unbalanced molecular equation, you would want to do what to it?
Balance it.
So then we're going to balance it by adding a 2. Like we just did right there, right? Simple enough. However, we can't stop there because now we need to go on to making it turn into a net ionic equation. So write out the complete. You can do that, or if you already know how to cross them out, you can write out the complete. But what you would notice is what's going to be soluble on both sides. The chlorides are. So they're going to spectate. So they're going to be crossed off eventually. Now, once again, once you will slowly develop to a point where you're going to be able to not even have to do this step anymore. You're going to see that and go, oh, soluble, soluble, cross it off. Don't even have to break them apart and do all that, okay? You will get to that point, hopefully. So cross off the spectators, write out your net. So that basic single replacement that you're used to seeing from last year really is a redox. And the net ionic of the redox is zinc solid plus 2 hydrogen ions that are aqueous. Will give you a zinc ion that's aqueous and hydrogen gas bubbling out of it. So you never thought you'd think of single replacement in this respect, but that is actually the net ionic of that equation. Yes? Because it's in its like solid elemental form, yeah. And then it goes into solution. So basically what you see is the zinc dissolving and then the bubbling of the hydrogen out. These are what I call simple redox equations, ones that you kind of know from last year. The ones that you're about to see me do here is a harder redox, like we're going to be doing in the titration lab, the redox titration lab. This is one where you're going to need water. Now, these steps are all written here for you, and I'm going to go line by line through the steps and show you how to do the first one, and then I'm going to have you try the second one, hopefully for homework, and bring it next time. So, a redox is now going to already be in its net ionic form like this. Okay, it's going to look funny to you. That doesn't look normal, right? You've never seen one like that. Well, they're going to give you reactions that look just like this and say, I want you to balance it. Now, the thing about balancing redox is, especially ones that have oxygen in it, you got to balance out the electrons, and that's important. But first, we need to separate them into their half reactions. So what I can see is the copper solid and the copper ion is going to be one of the half reactions. Those two go together. So I'm going to write out Cu2 plus over here. That's one of my half reactions. The other half reaction must be the nitrate going to the nitrogen monoxide, because those go together. They have the same kind of elements in there. Now, before I can move on to any other elements, before I can move on to the water and the O's, I need to check my elements. Do I have the same number of copper atoms on each side? That one's fine. I can leave that alone. The coppers are fine. The nitrogens, are there the same amount of nitrogens?
Yes.
So that's step 2. You need to balance all the other elements besides H and O first. And this is where it's going to get a little tricky. This side's pretty easy. Now I just have to add in my electrons. Okay? Which side did the electrons go from the copper? Since we went from 0 to +2, the electrons are kind of like a product being given off, so the electrons would go over here, right? That's where they were given off. That's why we have a +2 charge now on the copper. Does that make sense? So in this case, the electrons would be a product. Now, so that one's pretty much balanced on the left. That was the easy one. The one on the right has the oxygen, so it's kind of a pain. So in order to balance out my oxygens, I have to add waters until I balance it out correctly. So if I have 3 over here and only 1 over here, how many waters do I need to add? So I'm going to add 2 waters to this side. And this is these are balanced in acidic solutions. And as with the one we do in the lab, we're going to put acid in it to make it work. Okay. But now what did I do? I added some hydrogens randomly in there, right? But if we're in acidic solution, what are you going to have a supply of? Hydrogens. So guess what I get to add over here? Plus 4 H's. 4 H pluses, because we're in acidic solution, so there's going to be H's flying around in there. Are all our elements now balanced? Nitrogen's balanced, oxygen's balanced, hydrogen's balanced. Now I need to look at balancing the electrons. So what I do is I add up the charge. On this side, I have +4, because 4 hydrogens, right? A -1 from the nitrate. So that's a total charge of +3, right? Over here on this side, no charge on the nitrogen monoxide, no charge on the water, so its charge is a 0. So, +3 to 0, that means I need to add in 3 electrons. What side do they need to go on? I need to add in 3 over here, right? Because the +3 plus the 3 electrons, doesn't that make you get 0? A +3 plus -3 gives you 0, right? Okay, so this half reaction, I'm going to rewrite it down here to make it look right. See that? Okay, so that's my total half reaction. My other one was real easy because it didn't have any oxygen in it. Now, this is the key to the balancing of the redox. Look at our electrons. Are they the same? We have a 2 electron in the one half reaction. We have a 3 electron in the other one. We have to balance our electrons. So we have to do kind of these common multiple idea, which would be 6, right? So I would multiply everybody on this side by a 3. So I'm going to get 3 coppers, 3 copper 2 pluses, and 6 electrons, right? On the other side, I'm going to multiply it by a 2, right? This one's all going to get multiplied by a 2. So I get 8 hydrogens plus 2 nitrates plus 6 electrons gives me 2 nitrogen monoxides and 4 waters. Check me, make sure I multiplied through correctly, distributed correctly. Now, since our electrons are balanced, we have 6 and 6, right? Guess what they're going to do? They're going to cancel. And then all you have to do is add the rest together. So you just merge your reactants, you merge your products, and now you have your overall reaction. Let me get rid of this. Oh, didn't mean to do that. So I'm going to get rid of that line. I'm going to go back down. And I'm just going to merge the 2. So 3 copper solids here, plus 8 hydrogens that are aqueous, plus 2 nitrates that we know are aqueous, are going to give us what? 3 of our copper 2 plus that are aqueous, plus 2 of our nitrogen monoxide, plus 4 of our liquid waters.